Bon, merci. Bonjour à tous. Alors, aujourd'hui pour le séminaire solide, on accueille Thibault Roch, qui a en fait beaucoup de choses en commun avec moi parce qu'on a fait les mêmes études de génie civil à l'EPFL, on a eu les mêmes professeurs, on a eu aussi le même directeur de thèse. Et Thibault, depuis la fin de sa thèse, par contre maintenant est à Amsterdam. Il travaille avec Daniel Bonne et il va nous parler aujourd'hui de frottement et aussi de fluide à seuil. Et donc Thibault, floor is yours.
Merci Lucas. Déjà merci Lucas, Nicolas et Réginald de me permettre de venir présenter mes travaux. Je vais switcher en anglais pour faire la présentation, ce sera plus simple. So today I want to tell you about two topics I'm interested in. The first one is friction, and the other one is the behavior of yield stress fluids. So this research was funded by the Swiss National Science Foundation, but everything I'm going to present here has been done at the University of Amsterdam. So the first topic is the decrease of static friction coefficient with interface growth from single to multi-contact asperity. This has been done in collaboration with another postdoc at UFA, Liang Peng, my advisor Daniel Bonn, and Bart Weber, who is from also in Amsterdam, but from the Advanced Research Center for Nanolithography. So just so that everyone is at the same level on friction. So what is friction? It's basically the force that resists the motion between two contacting solids. And one of the most, let's say, important parameter in friction is the friction coefficient. Basically, the ratio between the force you put to have motion and the normal stress you are applying in your materials. But if you look at what happens at the interface between these two solids, where friction is developing, it's a really complicated physics problem. It's multi-physics because you have effects of mechanical loads, you have temperature, you have chemistry, you can have electronics, and it's also multi-scale because surfaces of your bodies are always rough, and so the contact between your bodies only occurs at some micro contacts, and the roughness develops over several scales. So in this presentation, I will only focus on the effect of mechanical loads and roughness, but it's already quite complicated. So as I said, surfaces are rough, they touch only at some small asperities, and it has been known for lot of years. The first, one of the first experiments that shows that was in between two plates of plastic from Dietrich. And what you see in this picture is the localization of the microcontacts at the interface between two pieces of plastic. And here you have experiments that are way more recent, done in the lab in Amsterdam, where we are using fluorescent molecules to visualize the contact between a silicon sphere and a flat silicon wafer. But what you can see in these two pictures is that your contacting interface consists of several discrete contact points, so that the macroscopic behavior that you are really measuring when you apply some force on a solid directly grow from a lot of contacting asperities. But it's really difficult to understand how one can go from the behavior of one single asperity to a macroscopic behavior. And that's what I'm going to try to present today. We did some experiments to try to visualize this change from single contact to multi-contact asperities, and to try to see if we can understand how the friction of this different system evolves. So to investigate this topic, we do experiments using a rheometer, so not usually used for friction experiments, but more for rheology. But what we did is that we take a silicon ball that we clamped at the end of a rheometer head. With the rheometer head, we can apply some torsion, so we can apply a really precise motion, and also we can apply some normal force. And below the silicon sphere, we have a silicon wafer that is clamped onto a cantilever and by changing the stiffness of this cantilever, we can explore different range of normal load. And we have a balance, really precise balance between, from which we can record the normal load we are imposing. And with this system, we can vary the normal load over 3 orders of magnitude. The sphere has a roughness of 40 nanometer. The wafer is almost flat compared to that. And we do the experiment in a dry chamber to avoid the formation of capillary bridges. So there's no water in the system. We conduct experiments that we call slide, hold, slide. So we slide for some time, we stop, and then we slide again. Why do we stop? It's to control the aging of the interface. In the case of silicon on silicon contact, when you let the 2 surfaces in contact, you will form more and more siloxane bonds. And so you will change the resistance of your interface. So the static friction coefficient will increase with time. So we control precisely the hold time, and we record a friction curve. Okay, so like the first slide, you hold for some time, and then you reinitiate the sliding. You have a peak, which corresponds to the static friction, and then it goes to some residual dynamic friction value. And we can do that for many different normal force, and that's what we did. And surprise, what we observe is that the friction coefficient over a large range of normal force is decreasing with the normal load. So for really small normal load, you have a higher friction coefficient than if you have high normal load. If we look in the literature and we try to find the smallest friction experiment that we can find, it's AFM, so atomic force microscopy experiments, and we actually have some data for the exact same system, silicon and silicon on dry conditions. It was done by the group of Rob Karpik. And we can find, so that's the new point here on top, a friction coefficient that is even higher than what we have in our system. And this value seems to align with our trend of decreasing friction coefficient with increasing normal force. We can repeat the experiment with a different waiting time. So instead of waiting 100 seconds before initiating the sliding, we only wait for 10 seconds. So that's the red data point here. And again, we have a decrease of the friction coefficient with increasing normal force. So now the question is, what's happening when we are going from low normal load to high normal load in our system where we have just a sphere on flat contact? So to try to investigate that, we propose a really simple model of a stick slip at the interface, where we consider that the interface between the sphere and the wafer is made of multiple contacts, as we saw previously. This is the case, but here we just divide the interface into some squares. Some are in contact, the one in colors, and they all sustain some normal load and contribute some friction strength to the macroscopic friction strength. And in our model, we just assume that the macroscopic strength of the ball on flat is just the sum of all the small contacts that we develop at the interface. To describe the behavior of each discretized contact, we assume that they will follow the microscopic friction behavior that was measured in atomic force microscopy experiments. So that's the curve we have here. And basically, we just prescribe a static friction and the dynamic value of the microscopic behavior. When we load the system, we consider that any shear force is just distributed homogeneously on the contacts. And when one contact fails, so when it goes over the static friction peak and so release some stress, we assume that this extra excess of stress is redistributed again homogeneously over the entire interface. So you think of this model as a fiber bundle model, but for the failure of asperities in friction. So in this model, the only things that can change with the normal force is the distribution of normal load and the contact map. Okay, so to estimate the pressure map, we did some numerical computation of elastic contact using an open source code that was actually developed by Luca here. And so we solved the contact of a rigid rough surface in contact with a flat elastic one. And into this model, we plugged in the topography of our silicon sphere and silicon wafer that we measured with atomic force microscopy. So here you have just an image of the roughness of the sphere. So what do we get? So we can make the elastic contact computation for a large range of loads. So at the lowest load that was used in the experiment, you see that the contact is actually one small contact, but as you increase the load, you start developing additional contacts up to a point where you have multiple contacts that make the frictional interfaces. So we really have a transition from single to multi-contact asperity. And we believe, and we will see later in the presentation, that this transition from single to multi-contact asperity is responsible for the decrease in the friction coefficient of such interfaces. Yes? Alors ici, on a vraiment mesuré la rugosité des surfaces qu'on a utilisées en expérience et on l'a mesuré sur différentes sphères. J'y reviendrai dans la présentation. Okay, so we are going from single to multi-contact asperity, and if we actually feed the results from the elastic contact computation into our small fiber bundle model, that's a shaded area in this plot, we actually find the same decrease of static friction with increasing normal force. And to compute the range of friction coefficient, we scan different spheres topography to get rid of the specificities of each topographies. So it's like there's like 3 different topographies shown here. So we have a good match between the experiments and our really simple model without the need for any adjustable parameter. We just took as an input the behavior from AFM experiment and the elastic contact computation. So now we want to understand how it happens. So if we can first look at the distribution of pressure. That's the first insight. If you look at the pressure distribution, when you have only a few asperities, you have something that is, say, more discrete in a way, because one asperity might have like a really high pressure distribution compared to the other. But as soon as you add more asperities in the system, you have a more continuous distribution of pressure. And in a sense, this means that for low load, when you have only a few asperities, that one strong asperities might dominate the entire behavior of the interface, while when you have multiple asperities, you have a more, less synchronized onset of slip. So asperities start sliding at different moments, and so the peak friction of the microscopic behavior cannot be seen. Okay, let's have a look at our model a bit into more details. Let's imagine we have just a single asperity, and we look at what we call the critical state, so the moment when we have loaded the interface, just before it starts completely sliding. If we have a single asperity, it will follow exactly the microscopic behavior. So the local stress ratio of our asperity will be exactly the static friction coefficient. Now if we add and this case, where we have a single asperity, is actually the limiting case of our model, because in the elastic contact computation, at one point, you will get to a single asperity, and you cannot have something different from the microscopic frictional behavior. And this is actually what explains this gap in between the IFM experiments and our model. Now, if we look at two asperities, there's two possible cases. The first one, we have one asperity that have let's say a small normal load onto it, and the other one has a really large normal load. When the low-loaded asperities will fail, the redistribution of stress is not sufficient to make the other asperity break. Okay, so the asperity with the high load will be able to reach its critical state and experience the maximum friction it can sustain. But the other asperity will be already at its dynamic value because it will pre-slide in a way. The other case is that when the first asperity breaks, the stress redistribution is sufficient to trigger the failure of the other asperity. Okay? And in this case, the asperity with the highest normal load is not able to reach its maximum contribution to the static friction coefficient. So in some sense, it's a subcritical, and it's not, and it can never reach the static friction. And in both cases, what you can see is that the addition of asperities that are not sliding at the same moment as the critical asperity will decrease the average friction coefficient, because in our model, the macroscopic friction is just the sum of the contribution of all asperities. In reality, the map of the normal pressure is much more complex than just two asperities. So let's have a look at the low normal load. In this case, you have many asperities. There's like 60 or 80 points in this simulation. And most of them have already slided at the critical state of the interface. And some of them, which we call the strong asperities, are still holding. But the presence of these pre-sliding asperities has decreased the macroscopic friction coefficient. The microscopic value was something like 0.9, and here we are at 0.7. If now we go towards high load, where we have a lot of asperities, actually, this effect is even more pronounced. We have a lot of pre-sliding asperities in the system, but we also have a lot of subcritical asperities, because at some point, you will get an avalanche-like behavior where the failure of some asperities will break the remaining of the interface. And in this case, you have a decrease of the macroscopic friction coefficient that is even more pronounced than for low load. We can look at it in a slightly different way. We can look at the fraction of the total normal force that corresponds to the critical asperities, the pre-sliding asperities, and the subcritical one. That's the curve here. And we can look at it as a function of the normal force. So when we have really low load and just a single asperity contact, there's only critical asperities. And we have a transition around the range of load that kind of corresponds to the range of load over which we have the decrease in friction. And over this range of load, we have a decrease in the fraction of normal load that is sustained by the critical asperities. So by adding more and more asperities, you create some asynchronous map of the onset of sliding, which reduces the macroscopic friction coefficient. This is the same thing almost for the friction force, just slightly different because the subcritical asperities might contribute different values. But yeah, the idea is that the addition of subcritical and pre-sliding contact decrease the macroscopic friction. So I will just summarize the first part of the presentation now. So we did silicon on silicon friction experiments with a broad range of normal loads, 3 orders of magnitude. And we observed a surprising decrease of the static friction coefficient. And in fact, we showed that it's related to the evolution of the interface from a single to multi-contact asperities. And we proposed a model that is really simple, but actually captures a decrease in macroscopic friction. This is analogous to a fiber bundle model. What controls the decrease of macroscopic friction is the distribution of the normal pressure at the interface. And the maximum friction you can have is controlled by how many of your asperities will be able to slide at the same time. So how synchronized the onset of slip at the interface is. I did not discuss that into details, but the range over which the friction decreases is controlled by the elastic properties and the roughness of your materials. If you increase the roughness, you will create much more contact at low loads. So you will switch the range of loads where you can observe this behavior. But we believe this is relevant for other type of systems, for example, a MEMS device, in which there's lower roughness, but also lower normal force, such that we can expect similar change in friction drop behavior. We also showed that the results remain valid if we change the microscopic behavior by changing the waiting time from 10 to 100 seconds, so that we believe that this result might apply to other kind of systems that are, where you can observe the transition from single to multi-asperity interface. Okay, and as I will switch to a completely different topic, maybe it's the time for question on the first part.
Est-ce qu'on a des questions?
Thank you, Thibault. I have a question about your comparison with the model from Tamas simulations.
Yes.
So I wonder how you can have a time effect in Tamas. What's the ingredient?
Okay, so there's no time effect in Tamas. The time effect is in the microscopic friction behavior that we feed to the model. In Tamas, so the elastic computation only gives us the normal pressure. But then, from the normal pressure, you get different strength. You get different strength depending on what you input as microscopic behavior. And this is the one that changes with time. That's the effect of aging at the interface. So in this, mu s and mu s changes. Yes, just mu s.
I have a question. So the distribution of normal pressures controls the decrease of the friction coefficient. So what happens if you have plasticity and your allegedly your distribution of normal pressure changes because of plasticity? You expect you will see also a decrease? Or?
So I think that if we add plasticity, we might see the opposite effect. But you will have some, like a high peak in the distribution of pressure where you have this plasticity. Okay, if you just imagine that you have like a saturated plasticity model, you might have just a peak at this value, and this will cause the macroscopic friction not to drop. Actually, in our experiments, we use, in our model, we use elastic contact computation because in our experiments, we do not see any change in the surface topography between the sphere, the pristine sphere, before the experiment and after the experiment. But yeah, if you add plasticity, you might have some additional effects.
The Coulomb law is macroscopic law in a way. No? So you use it at a microscopic level. It is pertinent or not?
Yes. So actually, this Coulomb law in this AFM experiments was really measured as a Coulomb law, right? You can see the drop from static to dynamic even as a AFM atomic force microscopy experiment.
But I don't see the dependence on the normal stress there. No?
Yeah, here there's no okay. Here there's no dependence
this
on the
point in a way because
so we use it as an input at this nanoscopic scale, right? But if you manage to do an experiment at the even lower normal stress, maybe there's a bit of change if you change the scale of your single contact. But here we assume that this is representative of the behavior of one single contact, that is the size of the AFM experiment.
okay.
Any other questions? Okay, I have a last one. So the aging in your system changes the value of the static friction coefficient. Does it also change the contact area?
No, so actually in silicon-silicon contact, there's no change in the contact area with time.
Okay.
So the aging is like the quality of the contact and not the quantity of the contact. It's different from like usual
but
aging.
There are simulations that show when you increase, because basically you increase the surface energy, and this sort of pulls the contact because of an increase of adhesion. And so you have a change of contact area, even though you don't have like any viscoelasticity or creep. And I was wondering if you could like sort of trigger, by waiting longer, if you could trigger multiple asperities to come in the contact and sort of like ride the edge between single asperity contact and multi-asperity contact just by waiting instead of changing the normal load. But
that's a good point, but actually I think like the change, even if there's like a small change, I think it's for silicon and silicon, it's not significant, that you cannot measure the typical change of a contact area with time.
Okay. Other questions?
Okay, right on time. To switch to the second part of my talk, which will deal with the behavior of yield stress fluids. So now it's a collaboration with a retired professor from TU Eindhoven, Thijs Michels, and my boss, Daniel Bonn. So again, let's start from the start. What's yield stress fluids? Usually, but not always, it's a dispersion of a material in a continuous phase. So you can think of soft particle suspensions, foams, or emulsions. And what is interesting with yield stress fluids is that their behavior might change depending on a lot of things. The first one will be the volume fraction of the dispersion in your continuous phase. There's actually a critical fraction above which the behavior changes depending on the stress you apply to this material. Here I take the example of mayonnaise. If you apply a high stress, you have a liquid-like state. When you press on the bottle of mayonnaise, it flows. But if you let it operate at low stress, it will have a solid-like state. So we have a jamming transition depending on the level of stress you're applying. Below the critical fraction, such materials behave as a non-Newtonian liquid. And if you look at steady-state experiments on such materials, they follow two well-known equations, which are Herschel-Bulkley for the flow of yield stress fluids above the critical volume fraction, and a cross equation below. And you have a smooth transition across the volume fraction, a critical volume fraction. So here you have a plot of castor oil emulsion with different volume fraction. You start with a high volume fraction. All these curves follow Herschel-Bulkley. And if you reduce the volume fraction, you get to the critical volume fraction and you go through the cross equation. And for the cross equation, you have an important scaling law as well, which is, sorry, this is not turned in. Yes, for the cross equation, you have an important scaling law, which is Krieger-Dougherty equation that tells you how the this Newtonian viscosity scales close to the critical volume fraction. And I'm showing these equations here because we can take some parameters, actually exponents from the steady state regime to try to understand and describe what happens out of steady state. So I'll come back to these equations later. So why are we interested in out of state yield stress fluids? Just from the previous slide, you've seen that they can have like different behavior depending on the stress you apply to them. And actually, when you do a complete, let's say, startup and loading of such fluids, they might show a lot of different behaviors. Actually, it will involve some creep deformation after loading. And the creep that is observed in experiments can have different kind of scalings. It can be logarithmic, it can be lower than logarithmic, higher than logarithmic, but always with a power law. And then after some creep, depending on the stress you applied initially, it can end up as a solid, so finite deformation, or you can fluidize completely your yield stress fluids. And this delayed fluidization is quite a problem because it can happen extremely late after you started loading your solid. And what we want to understand is how you can get the entire description of out-of-state yield stress fluids. Here I'm just showing you a few experiments to show you what I mean by the creep deformation and the fluidization. It's different materials. Here it's carbopol, protein gel, and colloidal glasses, but they all behave in the same way. You have a first regime of creep, and after some point, you have the fluidization with an increase, really fast increase in the strain rate, and a complete fluidization of the system. So the 2 points here is that we want to understand what happens during the creep. Yes? Above. Yes. Yes, yes. Because below it's only liquid. Yes. It's all above 5C. So what we want to understand is the origin and what controls the scaling of the creep flow and being able to predict the time to fluidization. So to do that, we developed a mesoscopic model for the description of yield stress fluids. It's actually an extension of a steady state model from more than 10 years ago from my colleague Thijs Michels. And it's based on the description of heterogeneous dynamics around the jamming transition. So it's an analogy to a critical transition between a stagnant phase and a fluid phase, like a second order phase transition. In this model, we have a single order parameter, which is a fraction of instantaneously stagnant particles. So particles in suspension that cannot move freely. We have the complementary fraction, 1 minus s, and we have a critical fraction that describes the transition from unjam to jam state. There's two competing effects in such systems. The first one is that if you apply stress, you can mobilize particles, so you can make particles that are stagnant escape their cage and start flowing. And you also have the effect of the heterogeneous dynamics and the fluctuation of stresses that can arrest the motion of particles. So you have a balanced equation for the order parameter S with the stress-induced cage escape term here. That is a function of how much stress you apply on your system and the distance between this stress and some barrier stress, that is the resistance of your yield stress fluids to cage escape. And you have the fluctuation induced arrest that depends on an exponent that is characteristic of the heterogeneous dynamics in your systems. So that's the main equation of the model. But we also have an equation that describes the viscosity of the model. And it's actually really similar to the viscosity as a function of the volume fraction. And the last ingredient of the model is how you describe the barrier stress. Okay, and we will come back to this in the remaining of the presentation. One important thing to note here is that the only parameter that we put into this model can be determined from steady state experiments. So you have the two exponents m and n. They are related to, so n, the exponent for the heterogeneous dynamics, is related to the scaling of the time to shear thinning in Herschel-Buckley and cross equation. And the exponent m for the scaling of the viscosity is the same as the scaling of the viscosity with the volume fraction. And the other exponent that I did not explain, the time scale are typical time scale for the attempt to escape a cage in one case, and the other one is a typical mobility time scale of the particles. Okay, so now what do we put into this model? What kind of stress barrier description can we use? So for non-edge systems, the relation between the stress barrier and the strain looks something like that. If you include only the elastic deformation of your particles. So if you start with no stress applied on your system, you can elastically deform your particles. So it's quite easy to make one particle escape because you can change the configuration of your yield stress. But as soon as all the particles have deformed and they create a structure, you increase the yield stress and it's more and more difficult to have a cage escape. So for this particular type of systems, we use this function that describes the elastic deformation of the particles. But in reality, a lot of yield stress fluids have a peak, a yield peak, that comes from structural aging or other reason, and in which plastic deformation are required to degrade the structure of your fluid before you can get to a fluidized state. And in this case, you have a peak here, and then you get to the dynamic yield stress value when you have completely broken the structure of your yield stress. And so in the next slide, I'm going to show you how the type of stress barrier you put in the model affect the different creep regime and what it tells us about the different creep regime that can be observed in yield stress fluids. So let's start with what is typically done in experiments for the rheology of yield stress fluids. It starts with a pre-stress. So you apply a high deformation to your sample to break all the effect of aging or any structures that you can have. And after some point, you drop the stress close to the yield stress, and you see what happened. So that's exactly the stress protocol we employ here. We have, so the red curve corresponds to the stress we apply. We get to a point where the barrier stress is almost equal to its dynamic value, and we see what happens. So here I'm showing you results of simulation. Let's first start with the plot on the top left. So this is a plot of the strain rate as a function of time. So at the beginning, you start rejuvenating your system. So you apply some stress. You make particles that were stagnant move, because we start from a point where the system is almost at the jamming point. So you start having particles that moves. After some time, you reach a steady state, so a completely flowing system at this really high stress. And then we drop the stress. And after the reduction in stress, we have a creep regime. So the red curve is, we drop the stress exactly at the yield stress. So the creep regime is infinite. And the other curves are final stress that are a bit above, right? So at some point you will enter again fluidization. Right, so we have some scaling here. And actually it corresponds to the scaling of the viscosity. Because in this case, we have a completely viscosity dominated regime because we break completely. So we already like pushed all the particles, so they are completely deformed, and what dominates the system is the viscosity. And you can look at the state of the system in a weird way here by looking at the balance between the arrest and the cage escape term in the balance equation. And actually, the value of this balance tells you if you are in steady state, so where both terms are equal and opposite, and the Andrade creep, where only the effect of the heterogeneous dynamics is stopping some particles. In this case, it's dominated by Andrade creep. Yes? Yes. Yes.
How is it related to tau A and tau B, the two microscopic designs?
So they are way smaller. So tau A and tau B are like 10 minus 3 or 10 minus 5. Yes. No. No, no.
And these don't depend on tau A and tau B?
So it depends on tau A and tau B, but not the scaling. So the time at which you will start observing creep or not depends, and the time it takes to reach steady state liquid depends on tau A and tau B, but not the scaling themselves. Okay, so in this case, when you break the entire system before dropping the stress, you have what we call viscosity dominated creep regime. And the fact that the exponent in the strain rate and the viscosity are the same is related to the fact that there's no change in viscous stress in this specific stress protocol, because we already reached the dynamic yield stress before dropping the residual stress. But now, what happens if we take into account all the elastic deformation of the particles? Because here, in some way, we just erased the shape of the stress barrier. So we can do the exact same simulation, but imposing a constant stress above or below the yield stress. And again, we have the same type of behavior. You have rejuvenation, then you have creep, and depending on the value of the applied stress, you have either fluidization above here or finite deformation. But in this case, the scaling of the creep regime is different. Before it was something like 0.6, minus 0.6. And now we have -1, so logarithmic creep. And this is due to the fact that now we have a combined effect of viscosity and a change in viscous stress due to the shape of our stress barrier. So instead of the strain, now I'm plotting the viscous stress, so the difference between the applied stress and the stress barrier. And we see that it also scales with a specific exponent. And actually, the scaling of the strain rate is a combination of these two exponents. And in this case, contrarily to what we had with the stress step procedure, we are not in Andrade creep for the critical loading, but we are in a really near steady state. So we always have a balance between the contribution of the cage escape and the heterogeneous dynamics. So in this case, it's really dominated by the particles deformation that we have logarithmic creep. Now let's have a look at plastic systems. And this actually will again impact the type of creep regime that you can observe. We do the same thing. We apply constant stress above or below the static yield stress. So now it's sigma c is a referent yield stress. Again, same thing. You start with some rejuvenation of your system. You have some creep. And now you have what is much closer to the experiments. You have a fluidization with a strong acceleration of the strain rate in one case, and an arrest of the strain rate for stresses that are below the yield peak. And again, in this case, you have a double contribution. So you have viscosity and deformation of your system, of your solid system. But here, it's not just the deformation of the particles themselves. It's some plastic deformation that corresponds to structural rearrangement of the structure of your yield stress. And we find some other exponents. The exact value is not really important, but what matters is that if we change how we describe the yield peak, here it's just a parabola, but if we decide to use any other shape that still creates a yield peak, we get the same scalings. Because what really matters in the creep regime is how we are approaching the top of the yield peak. And yes, we get some really generic exponents that are stronger than unity. So stronger than logarithmic. Now let's have a look at what happens with more realistic systems. So with aging, but with a step test procedure, because I said that yield stress systems might have a peak in their yield stress function, but it's not only due to aging. In some experiments, for example, in carbopol, you can try to erase the peak, but just the time between the first part of the experiment when you deform the system a lot and you start again the experiment, actually you will still measure a peak. So it's not clear exactly where does this peak come from, but it can also exist in systems where you think you erased it. So in this case, we, instead of applying like a really large stress and then dropping it, we just start from a condition that is a steady state Herschel-Bulkley for higher stress. So we have a different value of the order parameter, and then we apply a stress that is lower than this reference Herschel-Bulkley stress. And in this case, similar to the step stress case for elastic systems, you start with a viscosity-dominated regime because you do not have a structure in your system, but then you have a transition from this viscosity-dominated regime to a visco-elastoplastic creep regime. So a lot of exponents. I'll come back to a comparison with the experiments after to show you that they are actually observed in experiments and relevant. So yeah, here we have a transition from viscosity-dominated to visco-elastoplastic creep. The other quantity that is important is the time to delayed fluidization. And we can actually measure it in our simulations. Basically, that's the point of inflection from the cases with stress that is higher than the yield stress. And we find another scaling with yet another value of the scaling parameters. But this can actually be compared to experimental measurement of such fluidization time on two different materials. We have here carbopol and colloidal glasses. This is a plot from another study that also tries to predict the scaling of the fluidization time, and they do it by assuming that everything is near steady state, which we've seen in the previous slides is not always true, but anyhow, they still find an exponent that matches quite well the experiments. But we also find, with a different method, a similar exponent, which supports the validity of this scaling. So let's just have a look at different experiments, and we go back to all the scaling regimes we've seen. The most representative of what happens in real experiment is the one where we have a transition from viscosity-dominated to viscoelastoplastic creep regime. And that's actually what you see in carbopol. On top, you have the original figure in this paper of Thibault Roch, where he really insisted on this slope minus 2/3. which is the initial creep regime in his experiments. And actually, we predict something that is 0.6, so quite close. And on the bottom, you have the same data, but a bit extended, because actually something happens after outside of the figure that was not shown in the original paper. And actually, you have a change in slope, like the one we have in our simulations. And the slope here is something like minus 1.38, so quite close to the exponent that we predicted. And the exponents are predicted just based on the exponent of steady state. So it's measured in an experiment. We have the scaling of the viscosity. Again, in another paper, where we predict 0.6 scaling of viscosity, which actually corresponds to the scaling of all these systems. And we also find the scaling of the fluidization time as a function of the distance to the critical stress. So again, I'll just summarize the presentation here. So we developed a new model to describe athermal simple yield stress fluids outside of steady state, which was not readily available because a lot of people are interested only in the steady state behavior of such fluids. This model is based on the heterogeneous dynamics around the jamming point. And we can take into account the effect of the type of system. So if it's purely elastic deformation of the particles, or if there's a yield peak. We've shown that the imposed stress protocol might change the observed scaling, which is a really good insight to maybe conduct new experiments on such yield stress fluids to be able to explore either the viscosity or logarithmic and viscoelastoplastic creep regime. And I insist, all the parameters are just derived from steady state experiments. But yet we can predict the regime, scaling regime for out of steady state fluids. And actually, all the scalings I've shown in the plots are not just numerically verified, but we have some theory to predict them by taking some limits of the initial models. So yeah, we have the numerical confirmation of different scaling laws, the different type of creeps, that tells us some insight about which mechanism is dominant for Andrade creep, logarithmic creep, or viscoelastoplastic creep. We have fluidization and finite deformation, and also this nice continuous transition around the yield stress. So this is these results, they extend some previously published results of people interested in out of steady state yield stress, but where they took some limiting assumptions such as being always near steady state, so not purely steady state, but near steady state. And we are in agreement with them when they propose some scaling, but we extend the results to a complete description of the fluids. And this is a work in progress, but we hope to do more experiments on carbopoles to verify the different creep regime. We want also to add thermal effects because it's possible to go over the yield stress peak even if you are below, just due to thermal fluctuation in your systems, and that would be interesting to see how it can affect the scaling regimes. And the last things we want to do is to use these types of model for yield stress fluids and apply them to the description of earthquakes or frictional systems where you have gauge in between, because actually the transition from solid to fluid in yield stress fluids might be related to how you can describe the transition from static to dynamic friction in granular materials. And with that, I think I'm on time. And I thank you for your attention.
Merci Thibault. Est-ce qu'on a des questions? Pas de questions? Moi, j'ai peut-être une question du coup sur la partie plastique.
Ouais.
Dans la courbe verte que tu as montrée, tu as une réduction de la contrainte de la limite d'écoulement.
Oui.
Ça me fait beaucoup penser à de l'adoucissement dans un matériau élastoplastique. Du coup, est-ce que, là j'imagine, tu as un seul degré de liberté à ton modèle,
Mhm.
donc tu n'as pas vraiment de variation dans l'espace
Non, il n'y
l'état
a pas
contrainte.
de...
Donc,
C'est juste Minfield.
et du coup, est-ce que tu aurais, dans un modèle 2D, mettons, est-ce qu'il y aurait de la localisation possible du cisaillement dans ce genre de modèle?
Alors, en réalité, il y a de la localisation dans ce type de matériaux. Mais pour l'inclure dans ce genre de modèle qui est purement Minfield, ça me semble compliqué. Ce qu'on voulait faire, c'est peut-être mettre ce modèle dans des lois de comportement à une interface, par exemple, entre des éléments finis, pour que chaque élément ou chaque interaction entre contacts suive ce type de modèle, mais ça ne va pas permettre de localisation.
Tu as déjà localisé en fait.
Enfin, c'est ça.
Ouais.
C'est toi qui.
Ouais.
Donc ça me semble, avec ce type de modèle, ça me semble compliqué. Mais après, il y a des modèles plus développés où il y a vraiment les interactions de redistribution de stress, etc., qui
Ok.
peuvent faire ça, ouais.
Ok.
Donc, le fluide que vous considérez, donc j'ai vu en dessous de fissé, on a un comportement qui est visqueux non linéaire, c'est ça?
Oui.
Donc, en fait, vous avez un problème d'homogénéisation, vous avez un milieu hétérogène avec des particules élastiques. Mais vous mentionnez jamais explicitement en fait cette transition d'échelle. Enfin, comment est-ce qu'on peut décrire ces propriétés effectives? Il n'y a pas de référence à la microstructure. Donc, est-ce que vous connaissez des travaux où il y a ce type d'approches qui sont utilisées un peu pour décrire ces propriétés effectives?
C'est une très bonne question, parce qu'il y a des modèles qui... Donc nous, on ne modélise pas vraiment les particules, mais il y a des modèles pour les yield stress où il y a vraiment les interactions de particules qui sont prises en compte. Mais après, comment ces petits modèles, vraiment l'interaction, est-ce qu'on réussit à homogénéiser? Je ne sais pas. Mais si quelqu'un...
C'est une question aussi que j'avais. Les particules, vous parlez élastique, mais vous ne regardez pas la déformation élastique des particules microscopiquement. Parce qu'il y a des gens qui récemment, point clou, qui ont regardé le jamming avec des particules déformables. En quoi ça changerait ce que vous dites, le fait que les particules soient déformables?
Alors là, on cache le fait que les particules soient déformables dans la forme de cette barrière de stress, en fait. La fonction qu'on utilise, qui est une exponentielle en fonction de la déformation, prend en compte les déformations élastiques. Mais on ne regarde pas la déformation de chaque particule. Et du coup, on pense que le fait d'ajouter cet élément qui est censé représenter les déformations élastiques, c'est ça qui nous donne le creep logarithmique. Et dans son absence, on n'observe pas ça. Je ne sais pas si ça répond à votre question. Merci. Peut-être les yield stress, c'était